Hello, can you guys hear me? If you can hear, uh, a thumbs up would be great in the chat box. Hello, yeah, okay, okay, great, okay, okay. So, have you all downloaded the CrowdSource app? Yeah, okay, great. Yeah, some of you have downloaded the CrowdSource app. If you have not downloaded the CrowdSource app, uh, you can go to the link that is pinned in the comment section. If you want, I can put it once again, or you can just check the blue section in the comment comment box at the top. You can see a crowdsource.app a link, so you can follow that link and download the crowdsource app. So I hope we can begin the session because it's past 7:40. Okay, so yeah, are you all ready to attend the session? A thumbs up or any kind of emoji you would like would be great. Yeah, let's go. Okay, yeah, Aditya's all set. Okay, Abhiram, yeah, okay, yeah, let's go. Yeah, great. Yeah, okay, so okay, yeah, good evening all, and welcome to the second session of Explore ML with CrowdSource. Okay, I'm happy to see you all here, and it's our second session. Okay, so before we begin, I kindly request all of you to, if possible, have a laptop or a personal computer near you, so that we can have a hands-on session. Okay, so yeah, if you guys have the laptops with you, that's great. If not, it's still okay. You can use your mobile phones. Okay, so let's have a quick recap about what we learned in the previous session. Okay, so previously we had discussed about the basics of ML, wherein we learned about the rule-based uh, versus machine learning-based approach and the ML pipelines, AI versus ML versus deep learning, the differences, and we learned about the ML privacy, and we learned about the pretty basic concepts of classification, regression, clustering, sequence prediction, style transfer. Okay, we learned pretty much the basic concepts behind all these kind of uh, methodologies used in machine learning. Okay, so since you have gone through all that uh, set of knowledges, now let's dive into a new thing. Okay, so at times you might have often come across the term neural network, and some of you might have learned about artificial intelligence neural network simulating our brain and all that kind of stuff, uh, somewhere or the other. Okay, so these neural networks, they are a popular choice for machine learning models because of their ability to handle complex data and make accurate predictions where simple models might fall short. Okay, so let's watch a video. Okay, and you will get a kind of clear picture about what uh, the neural network means.
Hi, I'm
Can
Nat.
you hear the
And
audio?
I'm Lo. And
Can you hear the audio? Could someone put in the chat box thumbs up? Oh yeah, okay, you can hear. Okay, great.
this is our 20% project, where we go find out about different Google stuff we're curious about. Last year, we got to make a documentary about how voice search works. And that was the first time we heard about something called machine learning. Since then, we've been kind of fascinated by it. So today, we're talking with Greg and Chris to learn more about it. How would you describe machine learning to someone?
Well, there's a lot of problems that's really easy to solve with computers. Computers can go and simulate how galaxies move and how the courses of asteroids going and how close they're going to come to Earth. I could never hope to go and do that, but I can go and do this problem like recognizing that that's a tree, which is so much tremendously more difficult for a computer.
It doesn't feel like intelligence to us because it's so effortless as a human being to do it. But for a computer, it's actually really hard.
Because the real world is kind of messy and unpredictable at times. The strict logical rules that go into traditional programming just don't work.
Instead of going and writing programs that solve the problem, we write programs that learn to solve the problem from examples.
And it's this process of learning that allows them to improve over time and to actually be more clever than they would be if we wrote down a very rigid set of instructions for them to follow.
Machine learning is in so many different things that we use today that it's kind of like this invisible magic ingredient.
Phones with the ability to understand human speech.
Machine translation, email spam filters. When you go to the ATM and you give a check and it can read the handwriting. Or a Photos app that can automatically organize your photos based on the things that you like to take photos of. Like, here are all my mountain photos, here are all my food photos, here are all my dog photos, here are all my feet photos.
Everything from facial recognition to going and trying to recognize whether a particle is present in a particular collision at the LHC.
Which we would just like to take a time out to say is that big tube in the ground over in Europe that smashes particles together at really fast speeds so that scientists can use that information to unlock the mysteries of the universe, among other cool things. Now back to our episode, because I am getting really dizzy doing this. Ooh, ooh. So researchers and scientists are still experimenting and trying to find the best ways to teach computers how to learn. But a lot of the progress is coming from these algorithms that are based roughly on how the human brain works, and these are called artificial neural networks.
So an artificial neural network is something that it's a rough mathematical cartoon of how a biological neural network works. In a biological brain, we have individual cells called neurons. Each neuron looks at what its neighbors has to say and then decide what it wants to say. And in artificial neural networks, we have little mathematical functions. We put them in some organized structure, and then we say, okay, you guys all together, learn to do this task.
We have lots of neural nets that are really great at going and recognizing, this is a cat, this is a dog, this is a frog, this is a mouse, this is a horse, this is a truck, and things like that.
So take, for example, trying to recognize what this is.
So it used to be that we were really proud if we could get a neural net with 3 layers to work. And it's recently that we've made a lot of progress on techniques that allow us to train much deeper neural nets.
And that's why this kind of machine learning is also called deep learning. A neuron in the bottom layer is just going to be looking at a tiny piece of the picture and making some computations about it. It doesn't understand anything about dogs specifically.
But what the neuron does understand is it says, I'm giving a signal that's useful for somebody who's giving a signal, who's giving a signal, who's giving a signal, who's giving a signal.
They're kind of able to unfurl this really high-dimensional knot and pull it apart and make it easier to go and separate different things that are close together on the surface from things that were tangled all together earlier.
But then at the top, we'll put 2 neurons, and these neurons look at the whole picture so far.
They're basically experts at making the final call, figuring out, oh, all the layers below me said these things, so I know that this is a dog, or at least I'm 92.4% sure that it's a dog, so it's basically a dog. And while there's been a whole lot of progress with teaching computers to learn, they're still much slower learners than we are, and they make mistakes that you and I wouldn't.
So what I was working on is sort of trying to find a way to go and look at a neural net and ask, what does the neural net think the platonic ideal of a cat is, or the platonic ideal of a dog, or anything it can classify as? And suddenly you can go and ask, neural net, what do you think a cat looks like? And you get a picture of a cat, or neural net, what do you think a barbell looks like? So these weights. And it goes and it shows you a picture not only of a barbell, but of an arm attached to a barbell. So the model thought that the arms, it only learned what barbells were from looking at pictures of barbells, and they're often held by muscular weightlifters. And so it learned that there was, barbells have arms attached to them.
It takes them a long time to learn. You show it a picture of a school bus when it's early in learning. The very next time you show it a picture of a school bus, it's only a little bit more likely to say school bus. It doesn't get it, even though that was the very last thing it saw. Whereas, you say to a kid, that's a filing cabinet. And then a second later you say, what's that? Yeah. He's not going to be like, shoot, right?
Well, the more you describe this, the more I'm amazed by human beings.
Yeah.
The effect is wow, human beings are really amazing.
We're really amazing learning machines.
Okay, so you just saw the video. Yeah, we should be thankful for how great our brain works. Okay, so you just saw the neural network identifying a cat versus a dog, and then you saw a neural net trying to recognize a barbell, but still uh, the neural net kind seems to be thinking that the barbell always comes with an arm attached with it. Isn't it funny? Yeah, it's funny, I guess. Yeah, you might. Hey, people in the comment box, if you could just drop some emojis, it would be great. Okay, what do you feel about it? Neural net thinking that an arm is always attached with a barbell. Hey, people in comment chat box, people attending, a thumbs up or an emoji would be great so that I can know you guys are actively listening. Yeah, brain. Okay, Advait thinks. Yeah, he thinks he has a great brain than a neural network. Yeah, of course. Yeah, okay, okay, great. So by that we have got a very little bit of idea about what neural network is. Okay, so can someone just put in some definition, if possible, in the chat box? What do you think that neural network is? Okay, no answer is a wrong answer. Okay, so put in something that you think is kind of a definition for a neural network. Can someone? Okay, Advait, you have a big brain, so can you just put in some definition you think is something related to neural network, like what neural network is? Aditya, someone? Okay, yeah, you can answer anything. It's perfectly fine. Okay, there's no one here to judge you. Something that does some calculation for something else to do some calculation and so on. Okay, okay, calculation. Okay, I mean from what end? Okay, okay, okay. Wait. Yeah, all of you are actually right. Okay, so by definition, we could say neural network is something that learns on while progressing. Computer system to work like human brain. Yeah, exactly. Yeah, neural network works exactly like a human brain, but it's much bit slower compared to how faster we are. Okay, so it's like computer and processes like human brain. Yeah, yeah, it's yeah, that's also correct. Uh, processes for getting an output. Yeah, exactly, it's right. So next question. So what can a neural network do? You just saw an application of neural network identifying a cat versus dog and and all that sort of stuff. So what do you think is one of an application of neural network? Someone in the chat box, can you come up with some applications you think is an application of neural network? Okay, I think you're just confused what machine learning is. It's just confusing at times. Like we might confuse with machine learning with all the other things. Like you could say machine learning is different, not different, but it's kind of a superset of all the things. Okay, basically, an application of a neural network you could come up with is like okay, yeah, you could put something in chat box. If, what do you think is an application of neural network? Faster recognition and differentiation of objects. Yeah, that's perfect. Perfectly an example. Like yeah, it's an example of uh, neural network, an application of neural network. What neural computer vision. Yeah, we could say that, but uh, yeah, we could say that computer vision is also an application of neural network. But social media, yeah, the recommendation system, or we could say the advertisement, like using our own data to like advertise for ourselves. So I guess personalized ads, yeah, that's kind of an example of uh, neural network. We could say that, but yeah, it's also an example of neural network. Okay, so if you have any kind of questions, you could shoot out that in the chat section. Okay, so let's continue. So basically, what is neural network? Okay, we just saw the uh, distinguishing between the cat and dog and identifying these two animals. Okay, in the previous video. So let's just have a short definition on what is a neural network. So in short, it's a mathematical function that maps a given input to a desired output. Okay, just think that you want an output and you have an input. So it's just a function, a mathematical function that maps the input to the output. Uh, just imagine you might no, you have learned quadratic equations, right? So uh, let's just say these things in the basic and the most sensible way. Okay, so just imagine you are trying to solve a quadratic equation and you have the answer. The roots of that quadratic equation is let's say root 2 and plus or minus root 2. Okay, so the output is known and the input is a quadratic equation. So you're giving the input and you want the output, and you are putting in a mathematical function to find out the roots of the quadratic equation. So it's just simple as that. You have an input and you give the input to the neural network, and the neural network gives the output. Okay, it's pretty basic, and, and you could uh, easily understand what neural network is as we move on. Okay, as the introduction I just previously mentioned, we have learned about machine learning models such as classification, regression, etc. But uh, simple models work fine with simple data. Okay, uh, simple data that have much less parameters or much less, let's say that the much less data. So simple models work with very small amount of data. uh, let's say as soon as you want to interpret an image, you want to identify an image that have lots of pixels, let's say uh, a high resolution image with thousands of pixels, or an audio file with a numerous amount of frequencies, or even just a numerical data. Let's say, yeah, last day we had discussed about house price prediction models. So there are a numerous amount of variables that come into the place when you want to get the output. So dealing with these kind of complexity, we need something that has depth in learning. Like they need to have the context of what they are learning. Okay, so in neural network, simpler models are connected into layers. Depth of the deep learning comes from. Okay, uh, deep learning and neural network are often interchangeably used at times. So in reality, a neural network is a big, complex mathematical function which looks nothing like what you see here, but the diagram may help you see what's going on. Okay, so like any other machine learning system, a model is trained with data fed into the model, and it attempts to make predictions. Uh, at first, just as we have seen in the previous video, the model might make garbage predictions well, like the one we just saw. The barbell comes always with the hand, and that kind of mistakes the model makes. But we give the model a feedback that barbell doesn't come with the hand, so the model tries on improving itself, and later on, while improving and training more, the model becomes a perfect thing to identify for that specific task. So once the prediction quality is sufficient, the model is tested with new data, like the ones that the model have not received yet, and it makes a prediction based on what it learned from the training data. So, okay, so what this diagram doesn't show is how each neuron is able to learn and improve based on feedback. So this small diagram doesn't show that thing. Like uh, here it shows the prediction rather than the training thing. Okay, so let's dive deeply into how the neurons work and how that comes to an outcome, like it comes to make a decision whether it's a cat or a dog. So let's see. Okay, so here you can see some mathematical functions. Okay, uh, some of you might know this thing, but the other people who doesn't know anything about this, it's perfectly okay. So I just in, told about neurons in the previous slide. Okay, so just imagine that our human brain. Okay, our human brain consists of a large number of neurons. So neurons are each nodes that are in between. Okay, so you can see each layers here, and you can see so many dots in each layer. So let's imagine the dot as a neuron. Okay, so a neuron is each node, and one neuron connects to another neuron, that connects to another one, and another one, and so on, based on the amount of layers we put into this neural network. So to travel from one neuron to another, there needs to be some kind of a push or an activation. So for that we use activation functions. So that's in a high level overview. So let's get into the mathematical things. Okay, researchers describe the field of machine learning less like an engineering and more like a scientific exploration. So, for example, for a long time, the first function you see, the sigmoid function, was used until a ReLU or rectified linear unit function was discovered to be more efficient and effective in many situations. So, this is just a low level overview of what the neural network looks like the things behind it. So it's not necessary to know all of the mathematics behind the machine learning in order to use it. But it's shown here to reinforce the concept that machine learning is at its core complex mathematical functions rather than you just calling some methods or functions. Okay. So the mathematical function that is trained to do well on a particular goal. That's what the neural network or machine learning in a high level overview is. Okay, so if you have any doubts, feel free to shoot out the doubts. So we can just have a clarity on any of the topics that you have difficulty in understanding. So feel free to put in the chat box your doubts. Okay. So just as I previously said, uh, the activation functions. Okay. Here, um, okay. So for a neuron to be activated, there should be a condition that the neuron should meet before uh, going to another neuron. Okay, so basically, just have it in the basic form of view. Okay, so just imagine, uh, uh, yeah, let's take the academic system. Of course, the academic system that we all hate. Okay, so for us, needed to go to the higher level of education. We need to pass all our exams in the previous level of education which we were in. So here the situation is the same. Okay, there is a threshold set or a condition for activating a neuron. Okay, for a neuron to be activated or the neuron to be functioning perfectly, uh, the neuron should meet a threshold. Like the input that is coming should meet a threshold from the activation function, and if the threshold is met, the neuron is activated, else it's not activated. It's just a simple thing. So okay, so let's look at a couple of examples. Okay, yeah, here in the case we give an input 5, so our activation function is that the given value should be less than 10, then only the neuron will activate. That's what given in the slide. Okay, so the given number is 5, so when it goes through the activation function, which states which wants the input to be less than 5. So the condition is met, then the neuron is activated. Okay. So it's as simple as that. Okay. So I just want to remind I have a doubt. So are the activation? Okay. So Advait Narayanan has a doubt. Activation function on every neuron and okay. Are the activation function on every neuron and are they different as the layers progress? Uh, it depends on the type of neural network that's being designed. Usually, when taking the simpler neural networks that we learn in the beginning of our machine learning journey, we usually tend to use only a one new activation function for a whole neural network, okay, rather than going for multiple activation functions on different layers. But as things progress, the complexity, like when we are designing a large scale thing, the complexity often changes. Like um, so, at that kind of situations, we might use two different activation functions at different layers. But uh, for now, we only need just one function. Okay. I hope your doubt is clear. A thumbs up. Okay. Yeah. Great. Okay. So uh, that's one question. So let's have another question. Like, okay, here the question is very much different. Okay, we just given uh, a pixel of data. Um, okay, so the input is an image showing the number 7, but the activation neuron, what the neuron wants is no, sorry, the activation function is that whether the given image, let's say image of this digit 7 has a curve or not. So you can see there is no curve, right? So if it has a curve, then only the neuron gets activated. So here the activation function just simply is whether it has a curve or not. So here as the number digit 7 doesn't have a curve, it does not get activated. So this is an example of the rectified linear unit, the activation function. So I'll just show you. Okay, this is the function of the ReLU or the rectified linear activation unit. Okay, so let's go to the next question. So here the digit 6, whether it has a curve or not. So here the digit 6 has a curve as per the given situation. So the input does have a curve, so it passes through the test and the neuron is activated and the information is passed to the next neuron. So simple function like these can combine to make more complex decisions. So for example, the ability of the neuron to determine whether or not the input has a curve is due to other neurons checking to see, for an example, if a pixel is black or not. Uh, so it's just like that, checking one condition and uh, checking if the activation function is the threshold has met or not. If the threshold has been met, then the neuron gets activated. If not, the neuron does not get activated. So it's as simple as that. For now, you all need to know just the basic kind of stuffs. Okay. So as we move on further, you'll be learning more about this, and you'll get more uh, thorough knowledge on what neural network is. Okay. So here you can see neural network learning on recognizing a Labrador retriever. Okay, so you can see here a few sets of neurons uh, and two layers of neurons to be specific. So a neural network can be comprised of many hidden layers, as we have previously seen. So there are intermediate steps to get from prediction to the output. For example, a neural network may have layers to detect certain colors. In this case, certain colors in the pixels, and differentiate uh, between the and there might be other layers to differentiate between the certain type of animals or breeds. So it is important to clarify that the neural network does not know what a dog or a cat is. It's just learning to do what we want it to do based on the feedback and the patterns it detects. So basically, the neural network doesn't have the ability to think or do anything. It's basically our instructions that they have followed. So they keep on improving their uh, predictions based on the feedback that we give to them. Okay. So you might have been hearing a lot until now that the feedback, the neural network is getting feedback. And how does the neural network learn from feedback? So does someone have any idea how does a neural network learn from a feedback? Yeah, you can shoot your answers in the chat section if you think uh, this is how a neural network learn from the feedback. Someone? Back propagation. Oh, Aditya knows some stuff. Okay. Reinforcement learning. That's another stuff. But uh, yeah, we we could say, but still, yeah. Aditya has some knowledge on neural network, I guess. So he has got the back propagation, the fancy term of just going back and learning the stuff. Okay. So I'll say, okay, neural networks were, let's say, at the beginning were loosely modeled on after a brain's biological uh, function. Okay, the connections between the neurons can be either strengthened or weakened using weights and biases, which will come into the future slides. Okay, so for example, when a dog receives a treat and a pat on the head for retrieving a ball, it's more likely to do that again. uh, yeah, let's say it's like reinforcement learning, like you are rewarding someone for the good thing that they are doing, so it's obvious that that person might do more good stuff as they get a reward. Okay, it's just like uh, a human, let's say a child who uh, not not a child, a dog would be a better example because I don't guess a child making an experiment out of a child is a great thing. So let's say the example we just told, a dog receives a treat and a pat on the head for retrieving a ball. So that's a kind of way we could think of neural network. So let's say weights and biases allow a neural network to learn what pathways, uh, let's just say, work for a certain task, and biases the network to use this pathways again. So this makes the network more effective and efficient at making predictions. So it's basically that the weights and biases allow the network to choose on what pathways they should go. Uh, let's just say if the neural network identifies uh, a cat is a dog, and we just tells that it's not a dog, it's a cat. It gets the feedback that uh, the weight that it had earlier is just a wrong one, so it just takes another path and it tries to get another output. So at the second time it might be cat, so we say it's cat, so it fixes on that weight for that particular path, and so it gets the output as let's say the correct one, the cat and dog differentiation correctly. So but um, all of these complex calculations are accomplished far more quickly and often than a human could ever hope to do. So it requires a lot of computing power to achieve a high quality results, which is why neural networks were once thought infeasible, but now data centers, cloud computings, and high performance GPUs have all made it a reality for us to think about the neural network in much more easier fashion, let's say. So a great example is we are all using the great AI of our generation, the Chat GPT, for everything from doing our, let's say, all basic writing tasks. At least some of us have are doing that. Okay, so that's the power of neural network and the power the computing power has given to the uh, let's say the growth of neural networks. Yeah, Siemens too. Yeah, we all have done that, right? Okay, so in the previous session, I had told you to download some the application CrowdSource. So if you have downloaded the application, uh, you could you could have used in the last previous session the smart camera and the image label verification to identify the task. So neural network is a great example. Sorry, the smart camera is a great example for the neural network in functioning. So If you haven't done this, you could download the app now and try it out on your own. So we can just move to another thing. So have anyone seen this thing, the TensorFlow playground? Have anyone of you seen this thing? Uh, Thumbs up or thumbs down or something in the chat box would be great. Haven't? No. Okay. Yeah, Nikhil has seen that. Another person? No. I guess most of you have no idea on what the thing that you're seeing is. Okay. So no, but curious. Okay. Yeah. Let's discover what that is. Okay. So it's TensorFlow Playground. It's a thing that Google has set up for people to visualize on how neural networks works. Okay, so it's basically a machine learning. It's typically implemented using programming languages like Python, R. So specifically libraries like scikit, sklearn, in other words, TensorFlow or PyTorch, or let's say there are numerous amount of libraries that's available right now. So for those people who doesn't write code, there are APIs offered to make machine learning an option. So in this session, we are going to use TensorFlow Playground, a tool for exploring and learning machine learning without the need to write the code. Okay, so we will be exploring this in a moment. So here you can see a section, the output. You might have a little bit of idea what the thing that looks here is. It's just two different set of data, the blue one and the orange one, let's say. So Uh, while our goal with machine learning may be more interesting, like which of these X-rays contain evidence of cancer or not, so we'll just start with simpler. So our the goal we have right now is just to separate the blue and the orange dots. Okay, we need to separate these two dots. Uh, like we need to distinguish these two things, and we need to identify with our neural network that when a new data comes in, it fits into the blue one or the orange one. Uh, so do you think we could do this with just one line, like a single line that separates? Do you think, anyone in the chat section? Do you think that we could just separate this all? Yeah, we can't. Okay, no, we can't. So what would you need in order to successfully separate the lines, like the dots? What do you think would be an apt in this situation? Uh, some circle. Yeah, circle. Yeah, obviously circle, right? Okay, a circle which can be made by combining a bunch of lines, separating lines. So uh, we'll see that in a few minutes, like few minutes. So uh, here the case we are just seeing in the slide is a non-linear problem. So we always have, up until now, we have encountered with linear problems. Like we could say this or that just by looking with a just let's just say there are few distinguishable features that are easily identifiable, but in this case it's not easily separable. So let's say it's these kind of problems are usually called the non-linear problems. So so you can see the output in the 2D graph which we are seeing here, but the effectiveness of the model is measured with the loss. So the loss is the difference between your model's prediction and the data. So in general, the lower the loss, the better your model is. So we'll come into that in a bit. Okay. So on the left, you will see your features. So the features are the information drawn from your data examples, which distinguish one example from the other. So in TensorFlow Playground, which you are seeing this right now, these are just simply mathematical functions like vertical, horizontal lines, and their combinations. So the real world example for this might include, let's say we are distinguishing dog versus cat. So Our features might be the size of the dog versus the size of the cat. We'll be comparing that. We might be comparing the color. We might be comparing the length of the tail. Let's take another case like classifying numbers. So in the previous slide we just saw we classified 7 and 6 differently just by uh, analyzing if it has a curve or not, and the number of lines. Let's say you all had mentioned the thing about video recommendations or list recommendations. So let's say YouTube is recommending a video. So neural network comes into action, and here the features might be the video topic, the number of views, there might be the creator of video. Let's just say some famous creator and other famous creator whose video is being watched more. So these kind of features, the number of views, the creator of the video, the the demography of users who watch that kind of video. So these are the features that we often use to distinguish between things. Uh, so we were talking about the features that TensorFlow uses. So uh, the real world analogy which I just told could be easily like related to this. Okay. So the middle ones that you are seeing is the hidden layers that we just previously discussed, the different planes and that layers which, so these layers can identify the complex patterns within the data. So like yeah, that's just we could say in the simple words. So these neurons in the hidden layers can identify the complex things that are uh, in the data. So yeah, that's it. So we can learn about the TensorFlow playground in a bit. Okay, so you could go to this link. I'll put the link in the chat section. Okay, so if you are in that gone to that link, you could see a neural networks playground exercise. So as our first exercise, uh, okay, so in this exercise we will be training our first little neural network. So the neural networks will give us the way to learn nonlinear models without the use of explicit features we just discussed right now. So okay, so your task one is to run a two input feature into a single neuron. So and identify that if it can separate these non-linearities. Okay, so what we are just seeing here is the thing that I just said. We are trying to identify a non-linear set of data with just two input features. So let's see what happens. So here you can see epochs means the number of iterations that the neural network makes. So let's just reset it and let's just see if the two features can identify or just separate this uh, large set of non-linear data. Okay, you can see some gradients coming up and trying to differentiate. So it's just running. Okay, so it's just it can't identify on its own uh, with just two features with it. So let's just go to the task two. Okay, okay, let's increase the number of hidden layers from one to two. Yeah, we just have one hidden layer, so let's just increase it to the second one. Okay, now let's run. Let's see if it can form a distinguishing line or a pattern. Still, the model can't form. So, by the way, you should try on for yourself. Okay, I'm just showcasing the task, each task by task. So, if you have a mobile with you or a laptop, it could be easier for you to do the stuff. Okay, so we just increased one hidden layer. Sorry, I just increased two neurons. Sorry, hidden layers. Yeah, we have made two hidden layers. Let's just increase from two to three, maybe more. still the things are getting distinguished. Okay, so instead of adding more hidden layers, how about we add like more neurons? And let's just say we add more hidden layers with that more neurons. Okay. So it just isn't identifying, like differentiating the things. So how about we try increasing linear activation got skill issues? Yeah, of course. Linear activation functions are, let's just say, bad at sometimes. So let's just say change the activation function to sigmoid, which we just saw in the previous section. Let's run. So it just keep on getting like more and more complex, but it doesn't show the output. So let's check the answer. So yeah, this is what happens when we try to just do it with two features. So the activation function we just just it's linear activation function. So the loss is very high. The model underfits, like it can't uh, form a solution on its own. So for the task two, we have a non-linear activation function. Let's say, oh, it should use, okay, I didn't read the thing. Should use rectified linear unit, and we just need to try again. See, okay, okay, yeah, we got it separated, almost separated. Like most of the answers are coming up. So when we just use the rectified linear unit, we just were able to identify or distinguish these two set of things. So yeah, that's a great thing. Okay, we just tried adding two hidden layers. So how about we just reduce it and add more neurons with the rectified linear unit? Okay. Oh, that's great. So that when the activation function, three neurons in the hidden, yeah, it just acts weird when there are three neurons. So since we just have one hidden layer and a numerous amount of neurons, let's just say five neurons, and since we used the rectified linear unit, we got a significant change, like compared to the linear activation function. So that's the huge difference that the activation functions make in our neural network. So we could learn from just these simple examples that uh, often the activation functions we choose may lead to our things. Yeah. Okay. Do you guys have any doubts till now? Like we've gone through a lot of stuff. Yeah, how about we just reduce all the stuff and just a single neuron and a relay function? Yeah, it still can identify at least the orange part, a bit of orange part, which was previously not possible with the linear activation function. How about we add one more neuron? Yeah, it kind of identifies stuff, but how about we add one more? Yeah, it's kind of the solution. Like it's making the things much more easier, right? So that's the thing about uh, yeah, the TensorFlow playground. Okay, So we just completed the task. So add one more neuron. Okay, sure. Okay, add one. Okay, yeah. With just four neurons, we could just completely do the thing. Yeah, great, Nikhil. Yeah. Why was adding more layers not that effective computing? Okay, Advait, okay, we have got two questions. So I'll just answer to Advait's question first. So uh, the problem we had actually was that we were using linear activation function at the first. So even though we tried increasing the number of layers, or let's just say we tried increasing the number of neurons, the linear activation function can't just converge into the solution. Okay, let's just say it can't find the solution that we want it to find, just because the linear activation function can only, let's just say, uh, yeah, just imagine that you are just having a line equation, uh, but in this situation you can't separate uh, the non-linear things like I'll say, yeah, in this situation we can't separate these things. The orange one and the blue dots are pretty adjacent, and they are like staying up. The two orange set of dots are staying opposite to each other, so we can't identify like distinguish it with just one line. It's just not linearly separable. So in the case of a linear activation function, it just have a single degree equation. It's just like, let's say it's just a line that trying to separate a thing that's beyond a line. Line can be separate, line can separate. So that's what happens when we are using linear activation function. But in the case of uh, rectified linear activation function, uh, like we have seen earlier, it it's more than a line. Okay, so it can actually identify on what things can we like we can separate. It's like an exponential graph or something like that. Okay, so we have just played around with the playground, TensorFlow playground. So you can just go to the link which I had put in the chat box earlier, and try doing your own thing and trying to discover what the neural networks can do and what all things are possible. So try changing the activation functions, the learning rate, so you can see a significant changes that's happening. Okay, so let's just move on with the other things. Okay, okay, so yeah, we have seen about the TensorFlow and all that kind of stuff. So uh, let's do another task called L2 regularization. Okay, um, so, um, okay, just a second. I have a few doubts on that. So before the session ends, I'll give a clarity on what L2 regularization is. Okay, so it's better that I don't spill some rubbish things to you rather than clearing out the perfect parts. Okay, so uh, I guess we can continue with the rest of the portions, Aditya. Okay, sure. Okay, so let's just learn about the limitations that the neural networks have. Okay, so uh, in this experiment, I'll put in the link in, okay, teachable machine learning models. I'll put the link in the chat box section so you can follow along. Okay, so in this experiment, we are going to use Teachable Machine, another online tool for machine learning. So Teachable Machine is powered by MobileNet, a neural network that's been optimized for the site, so it can run on your mobile phones. It's great, right? All we had in previously we had discussed about the large computation power that neural networks require. So uh, Let's discover what the teachable machines can do. Okay, let's get started. Image project. Okay, audio project, post project. Okay, let's just take the post. Oh, okay. Sorry, I just thought you were able to see things. Okay, so let's get started with the teachable machine. Okay, go to the link and try it on your own. Uh, I'll give you around 10 minutes so that you can try it on your own. So while you try all these things, do take pictures and try to tweet or just put it in your LinkedIn that you had learned about teachable machine learning in this session, if possible. It's perfectly okay if you don't want to post your things in social media. But since we are learning some exciting stuff, it's better that we tell other people that we are learning things. Okay, yeah, let me try a few things. Let's just say you can uh, the thing here is that you can easily create a classification model, like you need to classify a dog and a cat without even needing to learn the actual machine learning things. So all you need to do is just give the type of images or the samples and train your model and then export the model, and you can preview, like you can use this model to identify these two classes. So if you are into some projects or things and you want the machine learning to identify two different things, or you want to add more uh, distinguishing things, like just say you want to identify a watch, a car, a pen, and all that, you can add those images here and add more classes and upload, train the model, and you can preview the model and export the model and use it anywhere else. So just try it on your own. Okay, so um, let me try things. Okay, so about the number of images, so uh, it depends on the type of images that you give. It's always good to give a good number of images, like a good number of samples, so that the model can get the pattern on how things would actually look. So the more the amount of images that you give, or the better the model works. Okay, so let's just say for your case, maybe if you are trying to identify dog and cat, maybe uh, let's just say at the least a 10 images or so would be great. But it's perfectly okay if you don't have that too much amount of data with you. But it's always great to put at least some amount of data to train the model. Okay, so let's just try. Okay, okay, you can try it on your own and see if you get anything, any outputs, and if you get anything good, uh, and you want to share it with others, just uh, put the message in chat box. So I'll give you instruction on how to share. Yeah, yeah. Okay, so yeah, let's try training our model. So I got few images. I don't think it would be great with just some few examples. So let's try to train the model. Okay, preparing to train the model. So have anyone of you tried training the model? Usually it's more than 100, but 50 is a good number. Yeah, okay, okay, yeah, okay, let's just try putting in some other images for testing. So let me just search for an image of cat. Okay, let's just see. Okay, okay. Let me just an image. Okay, yeah, it has identified it as the images cat. So that's great. We just had a good enough solution, a model with just very few set of images being trained. So uh, yeah, that's just an overview on how you can use teachable machines to recognize, just classify two different things or more. So like this, oh, memes. Okay, I don't think that it's easier to identify memes. Like there are a large amount of memes. So Aditya, could you share more on what you tried? What kind of memes you tried? If it's possible to share. Uh, one Doge memes. Oh, okay, okay. Maybe the model is already trained on identifying cat and dog. I don't know. So it was just easier for me to try it. So you can use your phone to train this machine learning model. So after training, you can just if you are training with something that's in your house, like let's say if you have a lot of cats with you, you can train with dog and cat, and at the end you can try using your mobile phone cameras to identify whether your cat is an actual cat or not. So try doing that if possible. Okay, so that's about the teachable ML. So try playing around. So okay, so yeah, we had discussed a lot about the teachable ML just right now. So let's just move on. So let's have a review on what we just learned altogether. So what is a neural network? So I just want someone of you to answer, what is a neural network? We have been going through the neural network, the term neural network, for a long time till now. So what do you think is neural network? Someone in the chat box, come on. And by now you might have had some idea on what is neural network. So uh, what do you think is neural network? Someone, come on. What do you think is neural network? What do you think? Mhm. Someone, please. It would be great if you could just put in something in the chat box and answer the question. Yeah, we had been a collection of neurons with activation functions connected by weights. Yeah, that's actually right. Yeah, that's right. Another definition. Someone else. Advait. Can you come up with something? Advait, Nikhil, Malavika. Okay. Complex mathematical functions to identify and distinguish certain letters. Yeah, it's also okay. Yeah. Um, one more definition would be great. Then we can move to next questions. One more. Come on, guys. You can. We're just about to finish all the things. Okay. Okay. And then I guess no one's about to answer anything. Okay. So then let's move on to next question. So when is a neural network useful? At what kind of situations do you think a neural network would be more apt rather than a simple machine learning model? Come on, shoot out your answers. Just it's just the applications. Okay, someone come up with some answers. Yeah, perfect. That's a perfect situation. Okay, just like Aditya said, we can't when it's used in situations when we can't just easily identify the distinguishing features or distinguishing factors that is in a let's just say our set of problems or our set of data. So uh, that's a situation where neural network is highly useful. So let's just move on to another other question. So what can it do that a simpler model might not be able to do? What do you think? Like we have been going through different type of things that neural network can do. So what do you think? Like uh, a simpler model, let's just say simpler rule-based model or just a simple machine learning model. A thing that a simple machine learning model cannot do, but a neural network can easily do. What do you think? Map more complex functions? Yeah, that's right. Okay, so someone else, can you come up with answers? Anyone who's still in the meet, who's still listening to my voice? Can you come up with some idea, answers? It's perfectly okay if you're going wrong because uh, nothing is ever wrong. It's just let's say it's just another type of interpretation you had on a thing. It's a perspective you have on a thing. I think so. Nothing is wrong. Nothing is ever wrong. So you can come shoot out your answers if possible. Okay. Okay. Yeah, Kalidas. Yeah, you got it right. Okay. That's another kind of situation. So we could use neural network instead of a simpler model. So yeah. Okay, so now I need all of the people who are in this meeting to just fill out a form that's I'm putting in the chat sections. So uh, fill out this form, and by the end of the session, I'll be giving another form, which is just within 8 minutes. You need to fill both the forms to avail certificates. So if you know someone who just left the meeting, ask them to join the session and fill out the form. Okay. Um, Okay, so while filling out the forms, I just have another question. So, what do you think is the limitation of a neural network or just ML in general? Since you have been learning things for the past few days about machine learning, so you might have a basic idea on what machine learning is or what neural network is. So, what do you think is a limitation of a neural network that has been bothering you from the beginning of this session or the previous session? Availability of a good training data. Yeah, of course. That's a huge limitation because it's the data that determines the quality of the output that we get. Okay. Another thing, uh, someone else, can you just come up with an answer? What do you think is a great limitation that could be one of that the ML models are being not being largely trained upon, like choosing models when you get started? Yeah. Oh, okay. Yeah. Uh, Nikhil just said fix the number of input layers. Yeah. Okay. Yeah. That at times it could be one of the like inhibiting factors in some neural networks, like unable to distinguish minute differences in data as provided. Yeah. For example, yeah. 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 Kalidas is perfectly right. Yeah. The neural network doesn't know what it is learning, basically. And it's not like us. They are just trying to recognize the patterns that are within the, uh, just say, an image. They are just trying to recognize the pattern, and upon feedback, they are like labeling that pattern and that path they choose as the correct one, rather than actually knowing about what they are doing. So the machine can't actually learn. Uh, but we always say machine learning. Even though we just say machine learning, the machine can't actually learn. They are just trying to recognize the patterns, and they are predicting upon the patterns that they identify. Yeah, there are the few limitations. Okay. Yeah, our brains are neural networks, but we have no. I don't really know about all the things about our brain. So our brains are so given a large enough network. Couldn't that limitation be out? It could, obviously it could, but the our current situation limits us from giving a large computational power to that these kind of neural networks. Uh, like uh, we can't say it's exactly like our our brains are exactly like the models that we built, but it's more like the models are trying. People are trying to build models that are more similar to our brain, but none of them ever achieved that kind of similar like the outputs that our brain our brain learns. Okay, so that's a big large research topic that people are yet finding things out on their own. So you could just google in and find many useful videos and articles, and even the google AI blogs, you could find people are trying to build more and more uh, accurate neural networks, let's just say AGIs, and all that sort of stuff based on the biological aspects of humans. So yeah, the limitations could be overcome, but the actual limitation here is the computation power that we could give for a single neural network to learn. So imagine us human beings, we have been living for, let's just say in my case, I have been living for around more than 20 years, and uh, the things that I know cannot be taught to someone else in just 1 year or just 2 years. So just imagine how much amount of data and how much amount of like just say uh, learning the model should have just to barely match our human being thoughts and processes. So that's a huge, let's just say, gap that we the brains versus the artificial neural network has. Okay. Yeah, that's a big topic for discussion. If okay, it's I guess it's a matter of experience, but we can't purely say that it's as these things are mathematical models. Basically, trying to find the best type of activation functions uh, based on the data we have is is the actual trick for identifying the number of layers and the neurons. So it mostly depend upon the data. So at times we can't just generalize a neural network for all the tasks. uh, each type of task require a specific type of neural network which has a certain type of activation function, a certain type of set of layers for distinguishing or identifying the features. So we can't just simply just say this is best for that and this is best for that. It just purely based on the data that we are providing as an input. And also at times if you are a developer, it's your experience that enhances you on choosing which model you want or which type of activation function you should use. So it's basically your experience and the mathematical knowledge that you have that helps you choose what kind of model you want. So since we have reached the time, I'm sharing the last post event feedback form. So once you fill this form, you're all set to have your certificates. So please do try to fill that form, and also make sure if someone who know who you know has just left the meeting, ask them to rejoin the meeting and just fill out the form. Okay. Oh, okay, okay. So it's perfectly okay if you have filled it. You will be availing the certificates. I try to make the machine and the present lesson. Okay. Yeah, Harimadhav, yeah, it's actually possible, but the thing is that if you are providing a huge amount of data, uh, let's just say, uh, yeah, you are giving a huge amount of data with people uh, with sunglasses and people without sun. Um, okay, I think you are trying to identify whether there is a sunglass or whether there is no sunglass, right? Sunglass or not? Yeah, okay, okay, I get it. So uh, the thing that just happened is in the beginning of the session we just told uh, we just saw a video where a person tried to identify a barbell with a neural network, but the neural network just gave the since the barbell people always hold the barbell and take pictures. The barbell, the neural network thought that the barbell comes with a hand attached to it. So that's the same situation that's happening here. So it's yeah, the sufficient amount of data that you provide would actually make the model more error proof, but still there are margin for errors to happen since you can't entirely train a model with all set of the niche possibilities that it's ever happened. So yeah, more data would lead to more less error model, data with less bias. Yeah, exactly, less bias. Bias means like yeah, just like the bias we actually use in our normal humanly world terms, being biased to something or being more favorable to something. That's actually the term bias means. So data with less bias. So if you give an like uh, let's say yeah, yeah, interesting. Yeah, sunglass people wearing sunglasses. Let's just say a cat wearing sunglasses, a dog wearing sunglasses, a chimpanzee wearing a sunglass. If you give all that kind of image, then the neural network might identify the fact that sunglasses are not always the thing that comes along with a human face. It's the sunglass that is actually the sunglass rather than a human face along with the sunglass is a sunglass. So try doing that. Maybe find a picture of a dog wearing sunglasses, a monkey wearing a sunglasses, and try giving that. Also, if possible, connect me with in LinkedIn and uh, tell me if that was did actually help you or not. Okay, so thank you all for attending the session, and I think that's a wrap up. So uh, now you have gone through the beginner track of Explore ML with CrowdSource, and CrowdSource is Google's platform for uh, creating a crowd-sourced database for creating more accurate and more powerful AIs for helping our needs and in Google products and things. So the difference or the contribution that you make to the crowdsource app is actually helping a lot of things to improve, and also helping things that you daily use like smart camera and all, lens and all that stuff, to become more and more improved. So okay, that's all about the crowdsource app, and thank you for listening to me for the whole 1.5 hour session. And I guess that's a wrap. Okay, if you have any questions, ping me up in my LinkedIn or anything that in LinkedIn or WhatsApp or any point of contact that you would like. Okay, so and thank you. So feel free to share your feedback in the forms that you receive in your mail about the session, so that we can conduct more such nice workshops or things. So thank you for listening. So bye bye people. Bye. Okay. Bye. Thank you. Okay, you are welcome, Nikhil.